The Big Bounce model proposes that the known universe began with a collapse of a previous universe, followed by a period of expansion known as the Big Bang. While it receded from consideration in the 1980s due to inflation theory, recent problems with that theory have renewed interest in alternative concepts, such as the Big Bounce, which offer potential solutions to issues like the horizon problem. The idea of a Big Bounce suggests that our universe may be one in an infinite sequence, or it may be the first iteration. However, considering the hypothesis of the primeval atom, identifying the intervals between bounces may be impossible due to the singularity in time at each instance. The quantum theory behind the Big Bounce proposes a change in the behavior of quantum foam as density approaches infinity, implying that physical constants may not remain constant, especially within a small time interval. Early proponents of the Big Bounce included Willem de Sitter, Carl Friedrich von Weizsäcker, George McVitie, and George Gamow. However, as observational cosmology improved, it became clear that a solution was necessary to explain the identical properties of distant regions of the universe. The inflationary period of exponential expansion in the early universe was proposed as a basis for inflation theory, which explained this phenomenon. Nevertheless, the universe continues to expand at a slower rate since the inflationary period. The concept of a Big Bounce in the early universe has gained support in the scientific community through a variety of publications dating back to the 1980s. While the origin of the phrase is unclear, it has been used to describe a universe that collapses and rebounds into a new branch, avoiding the singularity of the Big Bang. This idea has been explored in loop quantum cosmology, with results suggesting the existence of a previous universe that collapsed before rebounding. While some properties of this prior universe can be determined, others may be uncertain due to restrictions on fluctuations. The findings have been disputed by some groups. Despite ongoing debate, studies using numerical simulations have confirmed the main features of the Big Bounce theory. The theme of the story is a new theory that challenges the constraints of the symmetry of the affine connection and focuses on a dynamical variable called the torsion tensor. The coupling between torsion and Dirac spinors leads to a spin-spin interaction that is relevant in highly dense fermionic matter. This interaction prevents the unrealistic Big Bang singularity and instead produces a cusp-like bounce at a finite minimum scale factor, suggesting that the universe was contracting before the bounce. This theory also provides an explanation for why the current universe appears spatially flat, homogeneous and isotropic, and serves as an alternative to cosmic inflation. In 2012, a new theory of non-singular Big Bounce was developed, combining the benefits of matter bounce and ekpyrotic cosmology while resolving the famous BKL instability and forming a primordial power spectrum. Some speculate that this theory could explain the existence of distant supermassive black holes that are difficult to explain so soon after the Big Bang, like Euler's J1342 plus 0928, by suggesting that they were formed before the Big Bounce.